Hand-drawn images often exhibit stroke patterns that are organized in image space rather than follow the underlying 3D shapes. Such 2D patterns are useful because they provide greater visual abstraction. That means the artist can focus on what is essential and not distract the viewer with unimportant details. Because of this property, such patterns are effective at communicating and are widely used by artists when producing still images. In 3D graphics applications, however, these patterns pose a challenge. If applied naively, they produce a shower door effect where the pattern remains fixed in the image while the object moves behind it. We describe a new method for transforming image space patterns to move with the underlying 3D model. Here's how it works. In a pre-process, we generate sample points that are distributed over the 3D surface of the scene. At runtime, we use the image space locations of these samples in one frame and the next to compute the 2D similarity transform that best matches the observed motion of the points. We then apply the transform to the pattern. To decrease sliding for this model, we compute a separate transfer for the ears, head, body, and the tail, and then apply the same style to each. At the patch boundary, we blend the two patterns for seamless look. The similarity transform is a rigid motion with uniform scaling. The pattern expands correctly when we zoom in, but can eventually grow too large and lose its original appearance. To prevent that, we smoothly transition to a smaller copy of the pattern when the scale factor grows too large. For hatching, stippling, and painterly styles, we transition by alpha blending. For halftone styles, alpha blending is less suitable, so instead, we blend between halftone screens at the two scales. The pattern now morphs instead of blending. The blended halftone screens do not reproduce tones exactly like the original. Without tone correction, dark areas may grow and shrink during transition. Our paper describes a new tone correction method for halftone screens that fixes this problem. Our system supports styles that can easily be customized by the user. We'll illustrate the process for this halftone style. First, we load a 3D model, select the halftone shader, then define ink layers, each controlled by a separate light source. We choose a halftone screen and ink color for the first layer, and select tune shading parameters to achieve tone abstraction. We turn the backlight effect to enhance the silhouettes. Next, we add two more layers as highlights and adjust their placement by manipulating the separate lights that control each one. Changing the halftone screen is an easy way to create variation in a given style. Once a style is defined, it can easily be transferred to other models because 2D patterns require no parameterization. Now we'll show more examples of halftone, hatching, stippling, and painterly styles created in our system. This landscape scene contains several cow and horse models, a terrain, and a distant skybox, each rendered with our hatching shader. Each object in the scene is rendered as a single patch. As long as the camera moves gradually, the patterns move plausibly and have striking cartoon-like quality. This still life demonstrates our painterly style. Again, each object is rendered as a single patch. This running figure is divided into patches along natural texture boundaries and rendered with several halftone styles. Here we use multiple patches and blended across patch boundaries. Stippling style produced by our hatching shader that also uses multiple patches. While the transformed patterns can still exhibit significant sliding under some conditions, they produce quite plausible motions in many cases. This simple technique allows designers to incorporate image space patterns that are easy to create in animations and interactive 3D applications.